In this lecture, we'll continue our disk and washer method. So, well, we have some region. That's bounded by two vertical lines, and we have a line L. So, to compute the volume of the solid obtained by rotating my region S about the line L, okay? How do you do it? First, do what I just did. Sketch the region S and the line L in the same coordinate plane. Second, you are going to make a line that is perpendicular to L. It will intersect S with a line segment. So I don't want the whole thing, I only want the line segment part. Okay, this is corresponding to some x value from A to B, right? For any x, you make a vertical line, x equal, through this number, and then this line segment will be formed. If L passes through the line segment, you will have a disk. If the L, the black line that you're rotating about, is not intersecting with the line segment, the purple, okay? So like my case, the purple is away from L. When you rotate it, you're going to have a ring or a washer, because if you reflect it, it goes here. So when you connect them, it will be like this. Let me think about it. So yeah, it will be like this, and okay, this particular line will be like an annular thing with, so pretty much I'm having everywhere here, but not the inner part. Or if you just think you can open it on the side, so pretty much this is the center, and then here is the, let's call it Y1 to Y2, wherever that is. You have, when you rotate it in a plane, okay, they are supposed to be real circles. So you are going to have inner radius and outer radius. So when the line segment and the axis of rotation are not intersecting each other, if your line segment is away from the L, you get a ring, okay? And then the area will be the area of the whole bigger circle, pi times outer radius, minus the area of the inner circle, which is pi times r inner radius squared. If what you're rotating is part of the line segment, so let me draw another one. So instead of having that situation, say I'm having, let's just make it easy, something like this. I'm still rotating around my x-axis. So when I draw my vertical line, it will be this way. And when I rotate it, it will just become a circle. Like this, right? If you are getting a circle, then the area will just be pi r squared for the cross section. This pretty much this line. Imagine it has a little bit of thickness, and this line become a circle or a washer. That's pretty much what's happening in this section. So pretty much we are going to follow the 4 steps. Okay, let's see examples. Example 1, find the volume of the solid obtained by rotating the region bounded by y equals x and y equals x squared about y equals 2. So first we need to find the intersection point. That's where your x equals x squared minus x equals 0, x minus 1 equals 0, x equals 0, x equals 1. So here we are, we have x equals 0 and x equals 1 here. And we have a, maybe let me draw it a little bit further. I need to take this away too. Okay, so here y equals x and y equals x squared. I still have this region. And I'm rotating it about y equals 2, which will be here, 2. Y axis a little bit more. Okay, so I'm rotating this teeny tiny purple region around my black line. Although in reality what happens is this part will become, so this point goes somewhere here, right? So I will have a region like this, and oops, this will be twice much, so it will go here. Okay, let me at least not use purple, so you can still sort of see my drawing. So this point goes here, and the origin goes somewhere higher to 4, and you have one circle, and you sort of have the base circle, and the straight line, the y equals x, will be reflected into the inner part that you can't see, and the parabola is the outer part. So that's like the region. But actually, I don't really ask you to draw the graph so perfectly. I only need you to, I hope you can understand what's going on. Like, you know, you can visualize it. Even if you can't, you should still be able to compute it. Okay? So let me take away all my red. Don't think, you don't have to think the whole thing as a three-dimensional thing. Let's just follow the steps. Now we already sketched the region and the line. Now what do? You just pick some x. First of all, your x will, let me back off. You make a line perpendicular to the L, the rotation line. That's why I'm picking x values, okay? So I'm picking an x because I'm going to draw a perpendicular line to the axis of rotation, and I'm going to reach all the way to L. So here I'm having the inner circle, inner radius here, and well, use red. It's gray. This is the inner, R inner, and this is the R outer, right? So the line segment, the closer point to the L, the distance from the closer point to L to it is the radius of inner circle, and the further point to L is the outer radius. Then we can say we are having a ring. And what kind of ring? Let's see. So we know it's a ring. How far? This pretty much is the y equals 2. Okay, this is y equals 2. And your axis is like here. Oops, not really tangent to it. So the R inner is the distance of y, the difference of y. And that will be, this point is x, and this point is x squared. And this point is y equals 2. So the outer radius is from x squared to 2, which is 2 minus x squared, because 2 is higher than x squared. Okay, I'm just subtracting the y coordinates. And R inner is the distance between, well, the difference on the y coordinate from my y equals 2 and my closer point on this little red line segment, which will be 2 minus x. Okay, now let me just take away all these and put it under my graph. Okay, so the radius of inner circle is 2 minus x, and the radius of outer circle is 2 minus x squared. Then the area of the washer, A of x, is pi 2 minus x squared, the radius of the outer, minus pi 2 minus x squared, the radius of the inner distance squared. So this is pi times 4 minus, I hope you know the perfect square formula. It's a squared minus 2ab, so 2 times 2 times x squared, 4x squared plus b squared, x to the 4th, minus pi 2 minus 4x plus x squared. Same perfect square formula. So 4 pi minus 4 pi x squared plus pi x fourth minus 2 pi plus 4 pi x minus pi x squared. And then I see the 4 pi, and I'm sorry, this is supposed to be a 4. Yeah, the negative 4 pi cancels each other, and I'm getting pi x to the 4th power. I have that. X squared terms, I have minus 5 pi x squared, and finally I have the x term, 4 pi x. Then the volume is, notice our range of x is from 0 to 1. You have 0, you have 1, right? So the volume will be pretty much on this whole range. From 0 to 1, you integrate this a of x, and of course that's dx. Then it's just power rule, and we have pi x to the 5th power, and you flip it, minus 5 pi x to the 3rd power, you flip it, plus 4 pi x to the 2nd power, you flip it from 0 to 1. So this will be pi over 5 x to the 5th minus 5 pi over 3 x to the 3rd plus 2 and 4 get cancelled, you have 2 pi x squared from 0 to 1. Now plug in 0, you have pretty much all these coefficients. 1/3 plus 2 pi 1 squared minus, if you plug in 0, all of them is 0. I'm not going to copy the coefficients, but the whole thing is 0. So pi over 5 minus 5 pi over 3 plus 2 pi. And I guess I need to build a common denominator, 15. So this gives me 15 on denominator. This will be 3 minus, I'm multiplying 3 here, 5 here, minus 25 pi. And this will be a 15 top and bottom plus 30 pi. So I will do the plus first. 3 plus 30, 33. 3 plus 30, 33. minus 25, 8. So equals 8 pi over 15. That's the answer. Okay, so what I'm trying to show you is that it is good if you have the whole 3D object in your mind. Like you can picture it perfectly. It's like sort of like I don't even know. This is like a bowl kind of shape, but with no top or bottom. If you can see that, good. If you can't, just deal with the plane that you are having, the coordinate plane, where you draw all these region and the line of line of rotation. You should still be able to use this and washer method. Next example, find the volume of the solid obtained by rotating the region bounded by y equals x and y equals x squared about x equals -1. This time we are still using the same region as previous example, but we are rotating it around a different object, a different line. So x equals -1, right? So we are going to go here. Same thing from 0, 0 to 1, 1. And we have the line segment part from y equals x, and we have the parabola part from y equals x squared. And this time we're rotating it by x equals -1. So this is my x equals -1. This time I'm going to show you how you do it without even picture the whole thing, the three-dimensional object that you're having. Then I'm going to give you the shape, okay? All right, so I'm rotating around x equals -1, and I'm going to draw a perpendicular line to my black line, y equals x equals -1, which means I'm doing y, right? So here you go. You make a perpendicular line, and you're going to meet the region somewhere. Now I'm just going to draw nicely, okay? So instead of having a huge line, I'm going to take only the part that meet. This time, the line that you drew is horizontal, which means you're comparing x-axis. So you pay attention to x-axis, and if the line that you are drawing is horizontal, that means you're slicing your region that you're going to rotate into horizontal pieces, which means you are changing y. So it will be dy in your integral. Now, since it's dy, you are varying your y from this part, right? From 0 to 1. Now for a random y, this is the y. Sorry, let me give you my axes so you know this is where the origin is. This is x. I need to get this point and this point in y. Y equals x, so x equals y. Okay, y equals x means x equals y. This will be y, y. I'm writing everything in y because I'm slicing my region horizontally, or because my line that I'm rotating about is vertical, x equals something. When I draw a perpendicular line, it will be horizontal. So I'm changing y, and y is my independent variable. Similarly, when y equals x squared, my x equals, yes, in general you have two choices, plus or minus square root of y, but our side is the positive side, right? So we are taking the positive square root of y, or y equals 1/2. So here I'm having x as y to the 1/2 power, and y. And how about this point I'm having here? That's -1, y, x equals -1, and y is the same height. And you are comparing the x coordinate. So the r inner, let me put it, well, I'll just continue. R inner is the distance between, remember this is the region you are rotating, so it's from negative 1y to yy, right? So the distance is from y to minus 1. That's y plus 1. And our outer is, again, comparing the x coordinate, y to 1/2 minus negative 1, which is y 1/2 plus 1. Then, of course, your a of y this time will be pi, outer, pi to 1/2 plus 1 squared minus pi times inner y plus 1 squared. I'll do it anyway. Pi times, this is y plus 2, y 1/2 plus 1 minus pi y squared plus 2y plus 1. And this gives me pi y plus 2 pi y 1/2 plus pi minus pi y squared minus 2 pi y minus pi. So I can cancel the positive pi and negative pi, and I can track my terms. I'll do that. So y squared term, I only have 1. Y term, I have 2. And y 1/2 term, I only have 1. So I'm having the negative pi y squared minus pi y plus 2 pi y 1/2. Then I throw it in my integral. Y equals, remember, from 0 to 1, the cross section area dy. Now, power rule. Negative pi y to the third power, then, flip it a third, minus pi y second power 1/2 plus 2 pi y to 3/2 power 2/3, and evaluating from 0 to 1. This gives me negative pi over 3 y to the third power minus pi over 2 y second plus 4 pi over 3 y 3/2. I don't have much room, so we can just ignore the 0 part, I guess. Negative pi over 3, plugging in 1 gives you 1. Right, I'll keep it. Then I'll keep the power 2. Okay, this is my, 4 pi over 3, 1 3/2. Well, again, all these 1 to whatever power becomes 1, and the multiplication, they will disappear, minus whatever that will, 0, step in and become whatever, 0's power is 0, so the whole thing is a 0. This gives me negative pi over 3 minus pi over 2 plus 4 pi over 3. And this will be, okay, not too bad. When I do minus pi plus 4 pi, I actually get a 3 pi over 3. So this will be 3 pi over 3, which is pi, minus pi over 2. So it's pi minus pi over 2, which is pi over 2. And of course, you can just build common denominator 6. You will have the same answer. And as I said in the remark, in the previous lesson, we did do this question. But we did the same region. But in the previous lesson, we were rotating this region, bounded by y equals x and y equals x squared about the x-axis. So there are many ways you can do it. The same region, you can rotate it a lot of ways. So these two examples, including the example that we did for the previous lesson with this region, they are all washer methods, because when you do that cross section, you get a washer, which means the line segment, the cross section in the region does not touch the line of rotation. Next example, we are looking for the volume of the solid obtained by rotating the region bounded by y equals x to the fourth power. Sorry, y equals the fourth root of x equals 0, y equals 1. And then we're going to rotate it about x equals 0. Okay, let's have a basic idea what shape we are dealing with. Y equals the root function look like this. If you're not comfortable with it, think about it. When y equals the fourth root of x, you raise to the fourth power. X equals y to the fourth power. So it's a sideways parabola because y to the fourth power, even exponent. So you get parabola. And then you only, because you're taking square root, you only take the positive part. So half parabola. And then we have x equals 0, which is the y-axis. And then, maybe let me use another color so we can tell apart. This is y equals fourth root of x. And this is x equals 0. Oh, sorry. I'm having x equals 0. This is x equals 0. And I guess I'll call this 1. This is y equals 1. And we're looking at this region, and we're rotating it about x equals 0. Okay. So that's pretty much is the graph that you need to draw in the plane. Then, should I draw a better one? Well, I guess I'll just use this one. That means I need another color. As you can see. Okay, let's go with blue. I draw a perpendicular line to the line of rotation, and it will meet my region at 1, 2 points. This time one of the point is on the line, on the L, right, the line of rotation. So instead of having a washer, actually I'm having a disc. And then I just need the radius. So this is my y, and since this is 0, this is 1, y is between 0 and 1, and I need this distance, which is the x coordinate of this point. Y, what's x? Well, actually I solved it and I erased it. This point is on y to the fourth power, fourth root of x, and that means y to the fourth power equals x, or x equals y to the fourth power on this curve, in particular this point. Okay, so the r will just be the length, or y to the fourth power minus 0 if you want, because you are comparing the x coordinate of these 2 points that give you the radius, right? So a equals, sorry, let me say ay. For any y, ay equals pi r squared, which will be pi y to the fourth power squared. Wow, pi y to the 8th power. And then my volume is from 0 to 1, pi y 8th power dy. This will be pi y to the 9th power 1 over 9 evaluated. So pi over 9 y to the 9th from 0 to 1. That is pi over 9 times 1 9th power, pi over 9 times 0. Well, I don't really need this. And the whole thing is pi over 9. And let me show you, if you rotate it, what you get. So the curve you're having looks like this. And when you rotate it, you will have, well, first of all, you flip it, then you make the top a disc. Okay, so it's like it's really like a top, the thing that rotates, right? But it's circle everywhere. It's like this. That's the solid that you get. Okay, that's the section for today. Pretty much we are continuing the previous lecture. It's just that I'm trying to show you first, more washers. Second, how you can do it without really recovering the whole solid. Okay?